Good evening to you all to the second Chemistry AS session. Welcome back to those that attended last week. So there's a reversal of roles this week. You'll be led by Mr. Black this evening, who was responsible for answering your questions last time. So I will hand you swiftly over to his safe hands, and hopefully you find the session beneficial.
Okay, yeah, hello year 12. Right, topic 1.6. Hopefully you can see the syllabus on your screen. It's a big topic and there's lots of content. I'm going to attempt to do some of that content. I can't do it all, okay? Even my PowerPoint doesn't cover all of it because there is so much there. So without further ado, I'll get into the content. I'm just going to remind you that you have got the chat function there. So if you're not quite sure of something, I've gone through it too fast, you want clarification, do use the chat. Okay, so periodicity is topic 1.6. So obviously we're looking at the periodic table, and we start off with one of the most obvious statements. I'm not sure why it's even a learning point. Elements being arranged according to the atomic number in the periodic table, which obviously you can see 1, 2, 3, 4, and so on. It used to be in atomic mass, but no more. And then the next statement, which we'll explore to some extent, the electronic structures of the elements and relate them to their position in the periodic table, i.e. S, P, and D. Okay, so the first thing I've done now, hopefully you're familiar with this. This is a way you can remember your configuration. I just memorized it like a phone number myself, to be honest, but there you go. But I can remember using this when I did my A-level, which wasn't that long ago. Oh, maybe it's quite long ago. Yeah, but all I've done is I'll put the shells here, okay, and then you can use these arrow notation to put them into the correct sequence in terms of putting the electrons in. Okay, so there's our electron configuration that we'll be using a few times today. All right, that's the order they go in. So you've got the main energy level 1, the type of subshell, and the number of electrons that go into it. So we'll start off by looking at magnesium. So hopefully you'll recognize magnesium as being in the S block, and that tells me about my outer shell, right, or the outer energy level. So let's look at the configuration, atomic number 12. So if we look at our configuration, then we're going to write this, okay? 1s2, 2s2, 2p6, 3s2. Those are my 12 electrons. Now I just want to point something out to you. Whenever you do a configuration, always just quickly check your periodic table to make sure you're right, because its position in the periodic table should relate to your last energy level. All right, so look, energy level 3 tells me it's in period 3, which it is. It's in an S subshell, which it is, and it's the second one into that subshell. So 3s2 would fit, right? So the next thing then, it talks about ion formation and the electron configurations. So we can see, a very simplistic drawing of a magnesium atom. We're not showing the subshells here, okay? And hopefully you'll, realise that in order to become stable, get its full valency, magnesium would be losing 2 electrons. Where do those electrons get removed from? Well, if you think about subsequent ionisation energies, they're going to be the electrons that are easiest to remove, the ones that are furthest from the attractive pull of the nucleus. So it's going to be our 3s2 electrons. Okay, so now our configuration would look like this. This is our noble gas configuration, and that would be neon. Okay, so now we can look at this in terms of an oxidation process. So you know oxidation is the addition or removal of the addition of oxygen. You also know as well, hopefully, this oil rig, and this is where we look at electrons. It only works for electrons. Okay, so is this an oxidation or reduction? Well, if we look, the magnesium is losing electrons, so we could say the magnesium is being oxidized here. Okay, so let's look at chlorine. So we've got chlorine here in the periodic table, atomic number 17 electrons. So, I won't get you to write the configuration out now. Normally if I was teaching I would, but time is of the essence. All right, if you want to play this video back later and just see if you can write it yourself, that might be an idea. So that's our configuration. There's our 17 electrons. And let's just check the position of chlorine in the periodic table, and does it tally? Always, always check. Right, I should expect to find chlorine in the third period in the P block. So it is in the third period, it is in the P block, and I should expect to see the fifth one along that P block. 1, 2, 3, 4, 5. So again, you know, your configuration corresponds to its position in the periodic table. Okay. The chloride ion. Again, you know, you can see the chlorine's got 7 outer electrons, hence it's group 7. And there's our configuration as the atom. And you'll hopefully appreciate, to get its full valency, it will gain an electron. Now, I've just written this in a different way, because obviously we don't normally write chlorine as monatomic atoms. We usually write it as the diatomic. So I've just doubled up, okay, to get the Cl2. And again, hopefully, and we'll come back into this a bit later, there's so many crossovers in this topic that you can see at this time we have, there we go, there's the electron being gained, by the way. All right, so there you can see the electrons being gained. We've now got 18 electrons, so we've gone from 3p5 to 3p6. And hopefully you can see that that was a reduction. Now, the D block. The one the examiners love to ask because it's the one that's easiest to get wrong. Now, you can see I've written the configuration out like this, and this is how I started writing the configuration out to you, because this is probably what you're taught first of all. And that is that the s orbital of the fourth energy level precedes the d orbital of the third energy level. Okay, I actually don't like writing it like that myself, and I'll show you why in a moment. It's okay with atoms, it's when you form the ions that it becomes an issue. So you can see here, this is the way I would write the configuration out. However, when I put my electrons in, I always remember to fill my 4s before my 3d. Now I'll show you why that's important when we look at ions. Okay, so if we're looking at the ion and we're writing the configuration out for ion, I know already that iron's a transition metal. It should be in the D block. Okay, so let's have a look at our configuration. So this is how I've written my configuration out. Okay, 1s2, 2s2, and so on. And you'll notice that, as I hope you would do, you've filled in the s orbital before you've moved on to the d orbital. Remember, this d orbital actually holds 10 electrons. Okay, but when I got to this point, 2, 4, 10, 12, 18, so I've got another 8 electrons to go in. The first 2 go into the s, the remaining go into the d. Now you can write it the other way around. You can do it that format if you wish to stop you making that mistake, but I don't know. No, I think that looks better personally. And what I've also done there is just to remind you that you have to sometimes write the arrow configuration. So you can see here, first of all, I've got the shorthand. Okay, so I've got my argon, which is the element that precedes, or the noble gas element that precedes iron in the periodic table. And then I finished off with the configuration of the 2 highest energy levels, the incomplete, so the 4s2 and the 3d6. And you'll notice here, the reason I put this in is that you'll notice I'm not pairing the electrons up unless I have to. All right, so you can see that when I was putting these in, 1, 2, 3, 4, 5, my 6th electron, then having no choice but to pair. But don't pair them up, 1, 2. I can put 2 in there, 1, 2, 1, 2, 1, 2, so on. Okay. Let's just check its position in the periodic table. So here we can see in the configuration that my highest energy level is 4s2. Okay, so there's my 4s2, and there's my 3d6, and we should check where it is in this 3d block. So that's 1, 2, 3, 4, 5, 6. It's exactly where it's expected to be. And if you do ever get stuck with your configuration, you can also use the periodic table to help you. And I'll just run through that with you now. So you've got 1s, followed by 2s, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d. And there we are, 3d6. Okay, let's see how we get on for time. That's okay. So there you go, 3d6 is exactly where we'd expect. Now, writing the ions of a transition metal. Okay, first of all, the Fe3 plus ion. Hopefully you'll appreciate that that involves removing free electrons. In other words, oxidizing the ion. And I'm going to talk to you now about why I write my configuration the way I do. That's because when I form the Fe3 plus ion, I'm removing my electrons from the right place. Okay, so I'm going to take my electrons from the highest energy level, which once you've put your electrons in is the 4s. I know the 4s gets filled first, but once your orbitals are full, or you've put all your electrons in, the 4s is the highest energy level orbital. So when I'm removing electrons, I'll take from here first, and then if I need to, from the D block. So as a result, okay, you can see my configuration. The danger here is when you put your electrons in, if you, let's say you wrote the configuration out and put 23 electrons in, you're probably going to put them in the wrong orbitals. Okay, so I recommend what you do is you write out the configuration for the atom and then you knock electrons off it. Now, talking of knocking electrons off it, if I wrote my configuration like this is what I quite often see my students do. When they've written it like this, they see that as their highest energy level because it's the last one, and they knock their free electrons off there, and that ain't gonna do you very good. All right, so that's why I write my configuration out in the way I do. All right, so that's our covered our SPD notation and our ion formation. We've touched on there the idea of oxidation reduction as well. So the next thing then is patterns in ionization energies. Now, I'm not going to spend a huge amount of time on this. You know, you were probably taught this over a couple of lessons and you've got to see past paper questions. I don't want to go into that in too much detail. If you don't know your patterns, make sure you do. It's a common question. So there's two things you need to know about ionization energies. You need to know patterns across the periods, which is what we're looking at today. But you also need to know successive, which is where you strip electrons off from an atom. We're just going to look at the patterns. So here's our hydrogen atom. Ionization energy means the energy to remove this electron. Okay, make sure you know your definition, please, as well. Don't want to go over too much into your topic on ionization energies, but it's the amount of energy to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. So we're going to look at the factors that affect the amount of energy needed to remove this electron. Okay, so there are a couple of factors. The first one is obviously the number of protons, or what we call the nuclear charge. So as your protons increase, which is obviously going to happen as you go across your periods and down your groups, your nuclear charge is going to get bigger. All right, so that increases across your period and down your groups. You get more protons. Consequence of that is that increases the pull of the nucleus. So you'd expect your ionization energies to increase and get bigger in atomic number, but hopefully by now you know that's not the case, because when we're talking about ionization energies, it's not the nuclear charge we're interested in as such, it's the effective nuclear charge. And if you remember, that's the pull of the nucleus that the electron experiences, and it takes into consequence shielding. All right, and we'll have a quick look at that in a moment. So these are the factors, and then there you can see I've just added in there for you. This is all to do about your shells and where the electrons are. When you move into a new subshell, you're going to get a small decrease in ionization energy. When you move into a new energy level, like a 1s, well, 1 or a 2 or a 3, then you're going to get a big drop. And then finally, the other factor, which is you only get it at one point, is this electron pairing up. Okay, so this happens halfway across your P block. So for example, nitrogen is halfway across our P block. And I did mean to say at the start of this, might be a good idea to have a periodic table with you when we're looking at periodicity. But if you look at your periodic table, you'll see nitrogen halfway across the P block. And I've got the electron configuration there for you, 7 protons. And then we've got the next element along, which is oxygen, which is also in the P block, but it's the 4th one along. And you can see being the 4th one along, so we've gone halfway across, we're now moving into the second half, we've had to start pairing our electrons up. And we get this thing called electron repulsion, where the electrons will repel each other, and that lowers the amount of energy needed to remove that electron. So if we ionize this, it's going to be one of these electrons removed, one of the paired up. So let's look at the pattern. So we see this in the, you can see the 1s, so period 1, we've got period 2 here. Period 3 looks the same, okay? And I just thought what I'd do is just briefly, because I'm just going to check the time. Yeah, we're good. I'm just going to briefly go through what the pattern is. So you'll notice as you go across a period, your ionisation energies increase. And you'll know this is because your nuclear charge is increasing. Okay, so your nuclear charge gets bigger and bigger, you get more and more protons. However, you will see some drops. Okay, so it's not a steady increase in ionisation energy. Because of subshells, we have a slight drop. So when you go from your from your s orbital or shell to your p block, so you go from an s shell atom like beryllium to a p block element like boron, this is where you get your slight drop. So this is where your effective nuclear charge is less, and this is because increased shielding from a subshell. And then look, here's our nitrogen and here's our oxygen. Okay, this drop here is a consequence of moving halfway across our P block. Okay, so they're all dropped actually, they're all slightly out of position where we would expect them to be. This is a consequence of our pairing up of electrons. And what I've just done here on the PowerPoint, that's where there would be kind of bad photo editing there without that pairing up effect. And then finally, you can just see here, going from neon to sodium, we're going from a 2, energy level 2 to energy level 3, and this is where we see our big drop. Okay, so those are your patterns in the ionisation energies, and we can link this now directly to the reactivity of the elements. Okay, so we'll start off by looking at your group 1, and as you hopefully know from GCSE, as you go down group 1, they become more reactive. So you've got something like lithium here, which, for a metal is pretty reactive. It's sitting on the surface, it's fizzing. If you move to cesium though, which is a bit more spectacular, you can see well, how vigorous that reaction is. So why do they become more reactive as we go down the group? Well, it's because of how they react and their ionisation energies. So you should hopefully know, and we did mention it earlier, that a group 1 metal has got 1 outer electron. So when it's going to react, it needs to lose that electron. And you can see here, as we go down the groups, okay, or as we go down group 1, it becomes easier for that atom to lose its outer electron. And that, remember, is because if we go down the group, we're going into new energy levels, and there's a big drop in ionisation energy. Okay. So I've shown that for your group 1 here. Here's your group 2. I'm not going to read that to you. Okay, I don't believe in reading PowerPoints out. So why is it there? Well, you can read it later. Okay, that's something for you to have a look at. And I've just got a little illustration here just to show the idea of, this effective nuclear charge as we go down the groups. This is lithium. There's the first energy level shielding the electron. Okay, that's your 1s2. And then here's sodium directly below. And you can see here, there's your 1s2, there's your 2s2 and your 2p6. And you can see that we've got this increased shielding. That means this electron is easier to remove and explains the increased reactivity of that group 1 metal. So what are the reactions with water? Well, this is GCSE. However, I'm not going to make the assumption that you know. Okay, so This group, group 1, are called the alkali metals, and they're called the alkali metals for a very good reason. They produce alkaline solutions. That's the chemistry of group 1 and group 2. Group 2 are called the alkaline earth metals. All right, and you'll also know that when they react with water, they fizz, and this gas will actually combust if it gets hot enough as we go down the group. So, for example, with potassium, you start to see this lilac flame. That's your hydrogen being produced burning. So there you go. If you put your indicator in, you get to see this alkali nature of these reactions with water. Okay, and like I said here, you know, below sodium, the reaction is so exothermic that the hydrogen starts to burn or explode if it's produced fast enough. Okay, so the balanced symbol equation. You know, this is something that I would stress to you as a chemist, especially if moving into year 13. You've got to be able to balance equations. You've got to know your basic word equation and then turn it into a symbol equation. All I'm doing here is I'm using the ion sheet, and excuse me if you can do this already, maybe not everyone can. I've just combined my ions there, considering their charges. Okay, and then what we're going to do, once we've got our formulas, is we're just going to balance it up. So practice your balancing equations for me. Once you know the equation for one element in that group, so you could actually just memorize it if you wish. Remember, these are interchangeable. Group chemistry means these symbols can change. So if I wanted to do it for potassium, I just change Na to K. So that's your reaction of your group 1 metals with water. And then with oxygen, you'll know that these metals are stored in oil to protect them from oxygen and water in the air. And hopefully you'll know they'll form an oxide, which causes the surface to tarnish. So we never actually see the metal until we cut it. And if we just write our symbol equation, okay, there's our ions, the +1 and the -2 charge. Okay. And so then balancing it up. So you've got to know those equations. Now, I'm hoping as a chemist, you're not going to have to memorize them. You should be able to just use your ion sheet to write. Sorry, A-level, you haven't got an ion sheet. You need to memorize your ions. Group 1 +1, group 6 -2. So you must know your ions now, and then be able to use that to write your symbols, and then you balance your equations. Okay, and again, just symbols are interchangeable. Okay, so you can see I've done that with sodium. And I just thought I'd mention here as well, because it does mention it on your specification for 1.6, the flames that we'd see during these metals burning are the flame colours of these metals. So you see a red flame with your lithium, well, actually crimson red. All right, this is from a GCSE lesson, this one. I put red, well, actually, A-level. It's described as crimson red. Remember, strontium is red. Then you've got your sodium, which is yellow-orange colour, and your potassium with the lilac colour. Okay, so we're going to move on to group 2, and I'm not going to spend too much time balancing equations with you because there's other things that I'd like to look at. So here's our group 2. So we've got calcium and oxygen making calcium oxide. And again, you know, just like with group 1, it's the same thing. As you go down the group, they get more reactive. And you know that's because it's easier to lose your electrons, that decrease in ionisation energy. And I've just put here the flame colours. So you've got your calcium with your brick red. You've got your barium, which is apple green. You've got, as well, I haven't put that on there actually, and I did mean to, strontium, which is red. And then you've got magnesium. Now, magnesium doesn't actually produce a flame colour. When the electrons fall down from the higher energy levels, they emit light outside the visible range. What you actually tend to see with magnesium burning is plasma. Okay, so we're going to look at the reaction of group 2 now with water and steam. And there's a reason that we need to look at reaction with steam, and that's because, as we said, as we go down group 2, they're becoming less reactive. Okay, sorry, they become more reactive. I'm talking about the top of the group. So top of the group is less reactive. And so in order to get these to react with steam, we have to give them a bit of a kick to react with water, sorry. So here you can see the reaction of beryllium with steam. And you can see there, it's the same kind of reaction, but we form an oxide instead of a hydroxide. And we get hydrogen gas formed as well. Look at the temperature of the steam, by the way, to get the beryllium to react. 700 degrees C. There is another reason for that high temperature, but you don't need to worry about that. Now, with magnesium, a bit further down the group, so a bit more reactive, it will still need to react with steam. Okay, so but it doesn't have to be a really high temperature. And again, you know, you form your oxide and you form hydrogen gas. And there's an experiment that you can see where this reaction takes place. So I'll just put a picture here. And you can see there, you've got your magnesium burning, it's forming its oxide here. Okay, and if you look here, you can actually see the hydrogen gas being produced. And what we usually do when we produce that hydrogen is we just put a lit spill into it to burn it, just to show it being given off. Okay. So the rest of the group 2. Well, as we said, as we go down group 2, they become more reactive. So this is a picture here now of calcium reacting with cold water. And you can see, first of all, we're still getting the hydrogen coming off. Okay. But this time, instead of forming an oxide, with the water, we now form the hydroxide. Okay, so just give me a little bit of a break, have a quick think and bounce that equation. I'll give you a moment or two. I'll just check my time. Okay, so you'll need 2 waters. Hopefully you can see why. Okay, now the other thing I want to talk to you about here, and like I say, you know, I don't normally teach this topic, so I've actually, but there's a lot of crossover of points. I just wanted to look at this reaction. So we see the, you know, the calcium fizzing away, just like, you know, sodium would or potassium would. But instead of producing a clear solution, what I hope you've noticed is it's actually quite cloudy. All right, so it's not forming a solution as such. And I want to explore why. And to do that, we're going to look at now something that's mentioned in the syllabus, which is where we look at the pattern in the solubilities of the hydroxides and the sulfates. So you can see here's the pattern. Basically, as you go down group 2, you can see the hydroxides of group 2, they become more soluble and the sulfates become less soluble. And guess what? I always get that mixed up, or I used to, until I start to think about this. Barium sulfate. Now I know barium sulfate from its test for sulfate ions. All right, so this might link in some of your chemistry from other topics. The test for a sulfate ion is to add barium chloride and you form insoluble barium sulfate. So I now know in my head, when I'm trying to remember this order, that barium sulfate's insoluble. That tells me solubility of the sulfates decreases down group 2, and I know the hydroxides are the opposite. So whenever I'm not sure, I always just go back to my barium sulfate. So what's going on here then? Why is it going like this? Why is it cloudy? Well, the reason is we're forming calcium hydroxide, as you can see here, and it's sparingly soluble. So some of the calcium hydroxide will dissolve, so you'll have some of that calcium hydroxide in there. Hopefully you'll recognize calcium hydroxide as lime water, okay? But not much of it dissolves. So quite a lot of it is left as a kind of a precipitate, a solid. So you can see that there, that's why it's cloudy and not clear. So moving on. There is my test for a sulfate ion. Here you can see I'm testing sodium sulfate with barium chloride. And there you can see our precipitate of barium sulfate. So that's my little helper to remind me of the rules of solubility. Okay, and there you can see your white precipitate of barium sulfate. So using those solubility rules, then I'm going to get you to do a little think now. Barium chloride and sodium hydroxide, if I mix them together, would they be soluble? Would you form a precipitate, or would the products of those reactions be soluble? Well, let's just put our picture up here. Okay, just remind ourselves of the solubility rules. And let's think about what's going to happen. So if you're in my chemistry lessons in year 11 and in year 12, I've got a name for this reaction. We call them precipitations, but I call them do-si-dos. And do-si-do is a term used in country dancing, not that I'm a country dancer, by the way, for changing your dancing partner. All right. So if we were to have a precipitation reaction here, the metals would swap position. So we'd form sodium chloride, and if you know your solubility rules, all group 1 salts are soluble. Okay, so sodium chloride would most definitely be soluble. And then we've got barium hydroxide. Okay, so barium hydroxide would be the other substance that forms. And if we look here on our table or image, we can see as we go down that group, they become more soluble. So barium hydroxide wouldn't form precipitate, or this reaction wouldn't form precipitate. Now, I've also put this one in here because I haven't talked about the carbonates and what their pattern is in solubility. That's because I'm a bit lazy and I just see the carbonates as not being soluble. Okay, the only carbonates that are going to be soluble, if you know your solubility rules, are things like your group 1 carbonates or your ammonium carbonates. Okay, but let's think about our do-si-do. Let's change our partners. Okay, so we've got sodium sulfate and magnesium carbonate. So sodium carbonate, yeah, that would be soluble, group 1, no problem, but magnesium carbonate, not a chance. Okay, so let's think then about how we would write that as an ionic equation. So in the ionic equation, we're not interested in what we call the spectator ions. They will be excluded from that. And what you can do, you can write out the balanced equation, and then you can work out which are the spectator ions and cross them out. I never bother doing that. If I'm asked to write an ionic equation for precipitation, the first thing I think is, well, what's my precipitate? So my precipitate here would be my magnesium carbonate. So I use my ion sheet in my head to write that formula. Sorry about the 3, by the way, it should be lower, subscript, but there you go. And then I just think about the 2 ions that I would need in order to form it. So those are my 2 ions. And you can see I've used my state symbols, always use state symbols for precipitation reactions, AQ, AQS. Okay. So this is how you would write an ionic equation for a precipitation reaction. Just what's the form of the precipitate, what are the ions that you need to make that precipitate. Okay. So I've put this image in here for you, use it as you wish. I have put in the solubility of the carbonates, but to be honest with you, the carbonates, I just see them as forming insoluble, being insoluble group 2 compounds. And we've also got in here a little bit as well, the stability of the carbonates, and I think we've got the stability of the sorry, maybe not. Okay, but you've got your solubilities as well, and you'll notice as you go down the group, they form more and more alkaline solutions. So worth kind of memorizing that. And so now we move on to our trends in electronegativity. All right, so that's the pattern we see. We're going to just explain quickly why we see that trend. I just want to point out to you, your most electronegative element then is going to be fluorine. The other thing I'm going to point out to you actually is this definition. Well, I didn't want to do that. Bear me a second. Yeah, this definition. The exam board love asking definitions, and I think Mrs. Stevens mentioned that last week to you as well. Learn your definition for ionisation energy and this definition for electronegativity. And I really liked her advice last week, which was once you make it your own. All right, so make it something that you're comfortable to write. Make sure it's correct as well. So we're going to look at this trend. Okay, and I want you to link it back now to ionisation energies. they're the same pattern. And let's think about what ionisation energy is. Ionisation energy measures how difficult it is to remove your electron. Okay, so if you think it's difficult to remove that electron, you could also think of that as being, well, how much it wants to gain electrons as well. So the reason electronegativity increases in this kind of pattern is exactly the same really as the ionisation energies. It's all to do with your ability to gain electrons. Okay. So what we've got now then, we're going to look at the apply these electronegativities to the reactions of group 7. Hopefully you know from GCSE they become less reactive, opposite of group 1, metal more reactive, non-metal less reactive. They become less reactive, go down the group, and this is a very, very good video just showing those reactivities. I'll put that link there for you. It's very old, but it's very good, particularly when they show you the reaction with hydrogen. Right, so as we go down group 7 then, we're looking at electronegativity now, which we've kind of touched on. You can see the electronegativity decreasing, and we're just going to look at why that is. It's because of the fact that when we're trying, if you're in electronegativity is trying to get hold of electrons, how good you are. If we look here, this is the shell we're trying to put the electron in. It's right next to the nucleus. The effective nuclear charge is strong. This is fluorine, the most electronegative element. If we go down to something like iodine, we can see iodine. Look at all these shells shielding that nucleus. Although the nuclear charge is so big, the effective nuclear charge is not. Okay, so that's why it's less electronegative. So reaction of metals, that's your balanced equation there for something like a group 1 metal. And I wanted to talk to you now about this in terms of the chemistry, in terms of electrons. So hopefully you know that's ionic bonding, and you can see there's been a transfer of an electron from the sodium to the chlorine, resulting in the formation of your ions. And I was going to write this as a half equation now. Okay, so we could say this is what's happened to the sodium. It's gone from Na to Na+, it's lost an electron. You can write it like that, I prefer not to. Okay, that's this one's a more accurate way of writing it. And let's think about the chlorine. Well, the chlorine atoms gain the electron, so it's formed a chloride ion. And I'm just going to balance that out because we don't write chlorine like that, we write it as Cl2. And I hope you can appreciate now that this reaction is a redox process. And I hope that you can appreciate that the chlorine is acting as an oxidizing agent. It's being reduced. All right. So your halogens tend to oxidize things, i.e. take electrons from them. Okay, so summary as we go down the group. Well, I'll let you read that, okay, because I've already gone through that with you. But the point I want to make to you is you go down the group, they become less oxidizing. They're less electronegative. They're not so good at taking electrons away. And this finishes now here. I've got 1 minute left. I might go maybe 2 minutes over. That brings us on to displacement reactions of halogens. So what I've got here then, we've got some chlorine water, bromine water, iodine water, and we're adding various salts of the halogens to them, halide salts. And we can see that some of them have gone darker. All right, now that's a key observation with a displacement reaction of halogens. They always go darker, and that's because you're pushing a less reactive halogen out. Okay, so for example, with this one, chlorine water, I don't know, Ki, you can see the brown colour of the iodine being pushed out. As you go down the group, the halogens get darker. So just to finish off then, there's an equation for displacement reaction that you should be able to write from GCSE using your ions and knowing how to balance. I just wanted to look at it in terms of a redox process. Let's think about what we've got in here then. We start with chlorine, it becomes sodium chloride. Now I'm ignoring the sodium, it's just a spectator ion. So what's happened to the chlorine? Well, it's gone from a 0 oxidation state to a -1 oxidation state. It's obviously gained electrons, 1 for each chlorine. And where did those electrons come from? Well, they came from the bromine or bromide ion that we had in there. And if we think about what's happened to the bromide ion, it's formed bromine. How did it do that? Well, it lost electrons. Where did it lose them to? Well, if the chlorine took them away, the chlorine is more oxidizing. It's taking the electrons from the bromide ion. And that brings me, those are your half equations, what's happening in your displacement reaction. And there you can see just a little summary there. As you become less reactive, you're basically just not as good at taking electrons from things. You're becoming less oxidizing. Wow. So I went 1 minute over. I apologize. I haven't taught the whole of that topic. As you can see, there is a lot there, but I've taught the things that I think might need a bit more explaining. So I hope that's been helpful to you. And yeah, well, I wish you good night, and I hope to see you next week in the chat.